Shame on it. Okay, so Lewis structures, we know that we do the total atom counts based on their, not atoms, electron count based on their valence electrons. And however many valence electrons the total structure has, we have to depict that somewhere in the structure. You're going to place basically one bond, do what we call a skeleton structure, see if that's going to work, and if it's not, then you got to either add some double bonds, triple bonds, or lone pairs, or whatnot. Okay. Yeah. Come grab this one up here. It's just got electronegativity values, but it's close to. Hey, they did that last year as an April Fool's joke.
Oh yeah,
May and Luke. Yeah, they did that. That one's up there better. They can't. You don't do that. Don't do that. Okay. So remember, a sigma bond is a single bond, so you place that. Then if you need to do more lone pairs on the central atom, because everybody's got to get, how many? 8, except for anything under carbon. Okay. If the central atom is not yet surrounded by its 4 electron pairs, you can convert to pi bonds, but first of all, make sure it's something that can actually double bond, and that is these little elements right here, CNOPs. Those are the elements that can have multiple bonds. Carbon and nitrogen, they're special because they can also triple bond. Okay, and then the OPS can only double and single. Okay, so those can single, double, or triple. If you're carbon and nitrogen, if you're oxygen, phosphorus, or sulfur, you can double. Okay. Also remember that some things can expand their octets. If it's anywhere above what period can they expand their octets? In 3 or above, so 3rd period above. So phosphorus and sulfur like to do that a lot. Okay. All right. So let's do. They don't have what?
They're not able to.
Okay. So remember.
Can we stop using analogies?
No, we cannot stop using analogies. I can't teach without analogies. So, but don't write down some of the silly things I say. But if it helps you remember it, it helps you wrap your brain around it. Okay. But don't write down the silly things. Yeah, but I mean, to me, they're like people. The elements, to me. I am a big chemistry nerd. Say what? 108, yeah. 118 of my closest friends. Actually, some of them I don't really like very much, so, you know. I don't really like the ones in the F block that much. Yeah. Yeah. Remind me later when I'm not recording to tell you my analogy about the S, the P, the D, and the F group. I got a great analogy, but I don't want to record it. Hi, Mackenzie. We miss you. Oh, Landon, hope you're doing well on your quiz.
Old tree.
Okay, so let's draw some structures. We are so off track today. Maybe I shouldn't record this one. Maybe I should start over. Okay, so let's draw some Lewis structures. I'm going to open up another page because I can't draw in this small of a space. So I'm just going to give us a new page here so that I can. Okay. HF is the first one. So HF has how many valence electrons will I need to depict? I've got 1 here.
8.
Plus 7, as I'm going to have 8 valence electrons. So I'm going to draw my skeletal structure first, which is H bonded to an F. Okay. Remember, hydrogen can only get 2 electrons, so he's covered. But fluorine at this point only has 2, so we're going to go 1, 2, 3, 4, 5, and 6. So now I have depicted 8 valence electrons. Okay. All right. So the next one is nitrogen, which is one of our Brinkelhoffs, so it's N2. And how many total electrons would I need to depict there? 10. Okay. So I'm going to draw nitrogen, and I'm going to draw it like this, okay? So if I was to give nitrogen all of its lone pairs, what happens? How many do I have? I have 14. That's 4 too many, right? So let's try double bonding it. Now I'm going to take off these. Now what do I still have too many, right? So I'm going to take off these. Actually I'm going to take them all off and start over. I'm going to triple bond it, and then remember when we put lone pairs on there, we put them as far apart as possible. Okay? So that would be my Lewis structure for nitrogen. Nitrogen triple bonds. Okay. Now let's do NH3. Bonus, not really bonus points, just kudos if you can remember what NH3 is called. Ammonia, not ammonium. Okay. So I need a total of how many valence electrons to depict here? Is that someone's?
It's 8.
8 electrons total. Is that someone's? Okay. So we're going to have nitrogen.
Bonded to 3 hydrogens.
So we're going to put our, 3 hydrogens.
And then there's 2 more electrons in each.
I got it. There we go. So there's ammonia. We'll talk about geometry in a minute. Is it time to wake up or something back there with the alarm? Okay.
Wait, can you just explain like how you're finding the E?
Oh, okay. Here we go. We'll do it this way. 2, 4, 6, and 8. Because remember, each bond is 2 electrons. Because they're sharing. So 2, 4, 6, 8. Okay. Yeah?
Okay. You know how you said that carbon and nitrogen can triple bond? Can they only triple bond to like themselves, or can they triple bond to any other element?
They can so they can triple bond carbon and nitrogen together. A nitrogen can triple bond to a nitrogen, and a carbon can triple bond to a carbon.
Okay.
There is one exception of oxygen can triple bond, and that's in carbon monoxide. It is just an exception.
Okay.
Yeah. You know, because in chemistry we try to keep it fun with all these exceptions. So now we have methane. You should have methane memorized. Okay? CH4 is methane. So I'm going to need 8 valence electrons as well. So I'm going to draw carbon and give it 4 hydrogen. And I'm done. Okay? It's already showing 8. Each bond is 2 electrons, so it's already showing 8. Okay? I'm going to skip CF4 because CF4 is going to look just like CH4, except it's going to have F's in its place. And then you would have to put all the valence electrons around that. Well, let's go ahead and do it. So how many total valence electrons will I need here? 32. Because you've got 4 times 7, which is 28, plus 4 is 32. So it's going to look the same in terms of it's going to have 4 bonds. To make life easier, with the exception of carbon monoxide, carbon always gets 4 bonds, and it never has lone pairs, with the exception of carbon monoxide. The dots on this thing are tedious, because if I do it too much, it like tries to think I'm selecting them. So my dots are ugly. I'm sorry. There. So if I count all those up, I would have 32 electrons. Okay? And then, anybody want to give a go to the Lewis structure for, let's do, I forgot an important one. Okay, and that is the NO plus. From our rules, if it has a plus, what does that mean you're going to need to do? Take off an electron. So normally I would have 5 plus 6 is 11, but because I have that positive, I'm going to need to show 10 electrons. Okay, oh, this is another one of those exceptions for nitrogen. Yeah. Yeah, but you don't know that right away, so you're going to go ahead and draw it and say, oh, does it work? When in doubt, go ahead and draw everything. And now how many electrons would I be showing that way? 2, 4, 6, 8, 10, 12, 14. Too many. Okay? Matter of fact, 4 too many. So that's going to tell me I'm going to have to take off 2 sets of those lone pairs. So we're going to take them and say, never you mind. And we're going to draw another triple bond, and then I still got to take off some more, right? So take off those. So now I have 2, 4, 6, 8, 10. So, and then because it's a charge, I got to put some brackets around it and put the plus sign.
Wait, you have to have the brackets?
Yep, put the brackets around it and put the plus sign. Yes. Okay.
Is there ever instances where one of the elements has more lone pairs than the other one?
Yes.
Is that like with polar stuff?
Well, for instance, if something has a single, like let's say I'm bonding some carbon, and one carbon has a single bond and the other one has a double, and it would be different for each one. And we're going to see that in a second. We'll see it in a minute, okay? Especially when we talk about resonance structures, okay? All right, so those are those examples. The PCl5 I'm going to skip because I'll just show you this. It's going to look like this. Have all the chlorines and their lone pairs. And once you do all that, you should have all the lone pairs that you need. That's an example of an expanded octet. Phosphorus is in period 3, so it has the ability to do that. Okay? So let's talk about some other ones that are fun that you probably didn't see much of, and we didn't see much in Chem 1. So we're going to do exercise 8. Okay? So we're going to look at chlorine. It would be chlorine trifluoride. He didn't like it when he tried fluoride, but Okay, how many total electrons? Is there a charge on there? No, there's not. How many total electrons would I need? 4 times 7 is 28 electrons. Okay, so first thing I'm going to do is I'm going to take my chlorine. Remember, the least electronegative is your central atom, but even if you can't do that, it makes more sense that chlorine's your central atom, and you got 3 fluorines attached to it. So put your fluorines on there. Fluorine and chlorine do not have the ability to double bond in most cases. Sometimes chlorine likes to do it. He doesn't like to. He doesn't have feelings. Sometimes they can. How's that? It can. All right. So we're going to give fluorine its lone pairs because it still has to have 8, right? Yes. Aren't you glad I didn't give you these hard ones on that quiz? Okay. I don't think I gave you hard ones, did I? If you forgot the brackets, that is like 80,000 points off.
What? That's a negative grade.
Cameron, I'm going to need you to have like a signal with Donald whenever you know it's a joke. Just give him like a tap, give him a poke or something, and let him know it's a joke. Okay? Okay. No, I didn't see it. What message?
The HN double bond.
Oh, I did see that you got it, but after the fact doesn't count.
Okay, but
Too late.
It's like,
So you know we're not thought that.
It's the thought that doesn't count. That's for gifts, not for wrong answers.
Wait, that's just an excuse for people to be cheap on gifts.
Okay. So how many electrons do I have at this point? We'll count them. 22. I need. I think I have 24 at this point. Okay, good, because that's what I counted. So I have 24. So I have 4 extra electrons that I got to do something with. Okay, put them on chlorine. You are correct. I've changed colors to see if my dots will work better. So I'm going to put them there. Because remember, chlorine is above the third, or it's in the third period, so it has that ability to expand its octet. So it would look like that. And then the next one, XeO3. What? That's xenon. Why are we doing xenon? We're going to, yeah. Okay. Xenon is a noble gas. So we're going to attach the 3. Then we're going to give, I'm going to switch to this for this. Oh, that's so much easier. This is an actual thing. It's very explosive. Okay. Oh, we forgot to count. We needed 26, right? Whoa, that's bigger font so I could do my dots. But can you see that in the back? Okay, so how many do I have at this current time? 24. Okay. So I'm going to put...
It's 18. That's 18.
It's 18?
No, you asked how many we have right now, and we had 8, and it's 18. It was 18 currently until you put those 2 electrons on there.
Hold on. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now 26. I don't know where you're getting 18 from.
I'm sorry.
Okay.
I
Okay. So that is one. That is actually one possible structure. We'll find out later. There's another one, but that's a possibility. Okay. And so for our purposes, we would say, okay. We're counting up valence electrons. Is how we're doing that. Yeah.
Yeah, that's what we're.
Okay.
Okay.
Xenon has 8.
But the group to the left of that, like 4.
Remember the group. Remember it's the group number. Take off 10. Yeah. Okay. So that's that one, and then we're gonna do this one. Radon is fine. This is the last one we're gonna do, and then we're gonna move on. Okay. So I have radon chloride, so I have 8 here plus 14 for those two, so I have a total of 22 electrons I need to depict. So I'm going to draw my radon. I'm going to put chlorine. I'm going to put chlorine. Give chlorine. Oh, I went to switch for that one because I like these better. Oh, those are some big old electrons. I like it though. Easier to count. All right, how many does that show me? Well, first of all, I don't have enough on radon because he has to have 8, right? So I'm gonna go ahead and put some more on there to give him his 8. Okay. How many do I have right now? 20, and I need 2 more. So here, that I just do this, which doesn't make sense. From if I'd shown you this in Chem 1, you would have been like, what? But that's what radon chloride looks like. Count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay. My sweet little Chem 1 kids are still going 1, 2, 3, 4. I'm like, you can count by 2s. It's faster. Like twice as fast. Okay. Okay, so let's go on. So now you've got Lewis structures down, hopefully. So now we're going to talk about resonance structures.
Oh, I don't like
Why?
to draw like 12 things.
Good one, Jay. Okay, so these are this little section of the notes is very complicated, or lots of words to say that resonance structures are when you can't depict it only one way. Okay, if you can only depict it one way, then you're good. You go about your merry way. But if it takes more than one way to depict it, you have to show resonance structures. Okay, yes, we did. Resonance structures show up when if you have single bonds, it's not going to show up hardly. I mean, just because they're single bonds. But if you have like one double bond present and the rest are single, where do you put that double bond? If you have to ask yourself, well, how do I know where to put the double bond? That's your clue that it's going to be a resonance structure. And so classic example here is ozone. Ozone has one single bond and one double bond. Okay? And so how do we know if that double bond is between 1 and 2 or 2 and 3? And the truth is we don't, and so we draw it both ways. Okay? And then we indicate that with that double-headed arrow that's a resonance structure. Okay? In a little bit, we're going to talk about bond order. And basically, if you have a bond order of 1, you're sharing 2 electrons, 1 bond. If you have a bond order of 2, 2 bonds, 4 electrons. And a bond order of 3 would be triple bond sharing 6 electrons. In actuality, when you do the test on it, in actuality, ozone has a bond order of 1.5. Because in actuality, it's basically like 1.5 bonds. But we have trouble depicting that on paper, so we do a single and a double. Yes?
What's the bond order again?
We're going to get to it. It's going to be in the notes. I was just giving you a little precursor. Okay? So for resonance structure, you have to draw both. So let's do an example down here. Here's an example of the resonance structure for carbonate ion. Okay? Right here, there's a little note saying that they were supposed to have brackets, but they got left out. So If you don't have brackets on the AP exam, they're probably not going to give you your points. Okay, so let's figure out our resonance structures for NO2 minus, which is which ion? What's the name of that ion? Nitrite. Okay, so I've got a negative, so I'm going to need a total of 18 electrons. Do you agree with that? 5 for nitrogen, 12 for oxygen, and then plus 1 for that extra charge. So I'm going to need 18 electrons. Oh, that's still in the highlighter mode, sorry. 18 electrons. So let's draw this way. Okay. I'm just going to let you know you're going to need at least one double bond. And Emily, it was you that asked if you could have different amounts of valence electrons? And yes, you can, and this is going to be an example of that. So we would draw our bracket and say -1, and then we would draw our double-headed arrow, and then we're basically just going to put the double bond in the opposite place. Whoops, that's not there. Let's not go there, sorry. And so those structures are basically equal to each other in that they're both an equal possibility. So we don't know which one it is, so we draw both. Again, in actuality, you don't have a single and a double. You have 1.5 on both of them, but we don't draw it that way. Okay? Any question on the resonance structure? Okay. So that brings us to bond properties. And then we're going to hopefully, going to be tough because we're short on time, but I was wanting to get through formal charge today, which might blow your mind just a tiny, tiny bit, but it's not hard. But you might be going, what? But sometimes formal charge shows up on the AP exam because when we draw, like these resonance structures are basically the same, it's just switching. But there's some that are vastly different that are possibilities, and the way you determine which one is the possibility is you calculate its formal charge, and I'm going to show you how to do that. If I don't get to it in class today, I will do a flipped lesson on it and give it to you tomorrow when Mr. Norbrotten is here. Okay? So that brings us, this is a quick, I'm going to do this very quickly. This is not supposed to be here. That's in the wrong spot, so don't worry about that chart. Okay? Here's where we were talking about bond order just a few minutes ago. Someone go tell Landon his time's up. I think he accidentally got more time than you guys. I'm sorry.
Oh, it's okay.
Tell him to put his pen down. His time's up.
So curve points off.
Yeah.
Curve hours.
You accidentally got more time than they did. I forgot about you. Okay. Pick that up.
I was going to ask you a question.
I can't right now. I'm recording a lesson. Yeah. And I didn't answer any questions yesterday. Yeah. Yeah. We just moved on. So bond order is basically this right here. If you have one single bond, which is a sigma, and you're sharing 2 atoms, then it's a bond order of 1. If you've got 2 bonds, a sigma and a pi, it's a bond order of 2. And then a triple bond is a bond order of 3. Kind of makes sense, right? 1, 2, 3. Okay? This is like a fancy way of saying that, but the simple way is single bond is a bond order of 1, double is 2, and a triple is 3. That's why on that ozone, when it had a single and a double, we said that technically they're a bond order of 1.5 because that's an average of 1 and 2. Okay? Very quickly, bond length is that distance between the nuclei of the 2 bonded atoms. If you recall, it's where the minimum potential energy is obtained. But as you add extra bonds, so you have a single, it's the longest, double, and then triple is the shortest because they're pulling the nuclei closer together by those stronger bonds. So the shorter the bond length, the stronger the bond is. So the bond energy would be higher because it's a stronger bond. Okay? And do you recall from the thermochem, bonds broken minus bonds formed, right? That's going to show up again on this unit. The bond dissociation energy is the energy supplied to break a bond. Basically, it's bond energy for short. Remember that when we form bonds, what are we doing? Is energy being released or absorbed? When you form bonds, it's being released. Therefore, it takes energy to break them. Okay? Now, the overall delta H could end up being positive or negative, but it's going to be positive for forming and negative for breaking. So here's that equation. That M is supposed to be number of moles. So here's going, basically, I don't know if you figured this out. Normally we do products minus reactants, but when we're talking about bonds, it's actually flipping it. Okay? I don't know if y'all caught that when we were doing it. Okay. We are going to need all of these values right here. But I wrote them down on the next slide. So we're going to do this. Let's see if I can get it on the same page. I don't think I can. So we're going to do bonds broken minus bonds formed here. Okay? So if I look up the values for carbon-hydrogen bond, it's 413. But how many of them do I have? 4. I'm going to do it like this so you can see. 4 of them. For the chlorine bond, the chlorine to chlorine bond is 239. And if you don't have a calculator, go ahead and grab one out while I'm writing. And we have how many of those? 2. The fluorine to fluorine bond is 154. And we have 2 of those. In this one, we have chlorine to fluorine, which is 485. And we have chlorine to carbon, which is, where did it go? 339. And we have 2 of those, right? And then we have 2 of the HF bonds. And where did HF go?
No, you just put it over HF 3.
That's because I write too big. This goes, I'm just going in order of these. I can't write that small above that. So hydrogen to, this one is chlorine to carbon. Yeah. I was running out of room, sorry. 102, right? Is that what you just told me that? I didn't look it up.
565.
Oh, okay. I thought there
It's really hard to see.
Yeah, I'm sorry.
It's okay.
It's colored, like I said, if you want to print out colored notes, you can. I just don't, we don't have that kind of printer here. And then the HCl is 427. Okay? And then I've got 2 of those. So 413, 239, 154, 565, 339, and 427. Okay? So now we're just going to plug it in. So delta H is going to be equal to, and then we do our summation. So it's going to be 4 times 413 plus 2 times 259 plus 2,
239.
sorry, plus 2 times 154, and then that's all of our bonds broken minus our bonds formed. So we have 2 times 485 plus 2 times 339. I'm going to run out of room. Plus 2 times 565 plus 2 times 427. So when it's all said and done, we're adding here, so you shouldn't have any decimals, so you should just have a whole number. And when you do, you get, I gave it away right here, negative 1194 kilojoules per mole, which is endo or exo? Exo. Okay. All right. Next week, I think we're going to do it on Monday. We're going to do a molecular geometry lab where we're going to put together bond energies, molecular geometry, Lewis structures, and we're going to put it all in one thing together, and you're going to build molecules and do all this. But we're going to do it as reactions. It's going to be fun. That brings me to formal charge. Are you ready for formal charge? Yeah, but they're just, you know, business casual. It's just normal Lewis structures. They're casual. It's casual. Okay. Does everybody have this before because once I mark it, it goes away forever. Or until you watch the video. So maybe forever is relative. I can't get it back here. Okay. So, formal charges. And I apologize that we're having to do so many notes at one time, but I'm not going to be here the next 2 days, so we got to jam it in there. And we're up against Thanksgiving break. Okay? So, a formal charge is basically this. If there is more than one possibility for a Lewis structure, not resonance, because resonance is basically the same structure, just depicted if I have a single bond and a double bond. There are sometimes there's more than one possibility, and you're like, how do you know? And so last year, a couple of kids would come up to some of the structures and like, well, how do you know this one's not right? Because it works just like the other one does. So sometimes it's single or double bonded. So the formal charge helps you determine which is the correct structure. And the way, what you're trying to go for is whichever of the atoms in there have the lowest formal charge and still adds up to the ion, then that's going to be your winning structure, so to speak. So we're going to do with the SO4, we would do it with the xenon O3, but it would take us a really long time. And so I'm going to that's going to be your challenge one to figure out. Okay. So the way that you calculate formal charge is this. First of all, this should be 1/2 of the bonding electrons. It's a typo. Okay. So you take your group number for your atom, and you subtract from it the number of lone electrons, so the number of electrons that are in the lone pair, and then half of the bonding electrons, because remember, only half belong to that particular atom. The other half are being shared. Okay? You use it to determine which resonance structure is correct, and then atoms should have as small of a formal charge as possible. The closer to 0, the better. And then if it is a charged ion, you got to meet the charge of that ion. Okay? So let's just dive right in. So we're going to draw all the possibilities of sulfate, SO4 2-. I'm going to add an extra page because I cannot fit it in that little space. Okay, so SO4 2-. So how many total electrons am I going to need to depict here? I got 5 with 6, so that's 30, right? And then I've got a -2, so I'm going to need to depict 32 electrons. Okay? So there are a couple of there's basically 2 possibilities. You've got this way. Why isn't it not showing up there? Oh, it's reconnecting. I'm sorry. It's thinking. Y'all can't see if it says reconnect. No, if I do that, it will stop the recording. Yeah. Okay. Okay. So here we go. Now you can see it?
Yeah.
So we're going to give everybody its lone pairs. I still wrote too big. I'm still going to run out of room. Okay? If you were to actually look up, this is another possibility. So we do our double arrow. Another possibility is because sulfur is able to expand its octet. You can do this. Now, this would have the resonance structures along with that, the double bonds. But that would take too long. And that is unfortunate that the bell rang. Okay.
Yeah, 2 days in a row.
Because we're going bell to bell instruction. That's what I get paid to do. All right, I'm going to do a flipped lesson on the rest of this and make it for you to watch tomorrow. And then I'm gonna go through the molecular geometry and polarity, and then you're gonna get a worksheet on drawing those and determining polarity and geometry.